Hey everyone, welcome to The Explainer. I am absolutely thrilled we're diving into this today because we are looking at a highly complex but just fascinating AI solution to a massive global problem. We're talking about rivers, rainfall, and the neural networks that are actually helping us reconstruct missing hydrological data, which, by the way, can literally save lives. So get ready because we are unpacking some serious brain-inspired machine learning today.
Okay, let's dive into this. Picture this. How exactly do we manage global water resources when the data we desperately need, well, it simply doesn't exist? It's a huge, high-stakes reality. All over the world, the mathematical models we use to predict droughts and floods, they rely on continuous streamflow records. But out in the real world, data collection is messy. Sensors break, storms wipe out entire equipment setups, and suddenly we're left with these massive blind spots in our data. So, here's our roadmap for today. We're going to cover the missing water data crisis, how brain-inspired AI steps in, the SNN-ET super team, the ultimate data stress test, and finally, the future of global water management. Section 1. The missing water data crisis. When the river runs dry, on paper. If we look at places like the data-scarce southern basin of Thailand, it becomes really clear that missing data isn't just some annoying spreadsheet error. When hydrologists look at a river's history and literally just see blank spaces, it directly cripples our ability to predict catastrophic floods or manage severe water scarcity. Think about it. If we don't know how much water was flowing yesterday, we definitely can't accurately warn a downstream community about a flash flood tomorrow. Because let's face it, gaps in the data, they're completely inevitable. We're talking equipment malfunctions, administrative hiccups, natural disasters washing away sensors, or just having really sparse gauging stations to begin with. And since we can't completely prevent this data loss, hydrologists are forced to impute, which basically means mathematically estimating and filling in the missing pieces, rather than just throwing out the incomplete records. But doing this accurately is incredibly hard. Section 2. Brain-inspired AI steps in, the temporal hero. So, to solve this massive imputation problem, researchers brought in what I like to call a temporal hero, the spiking neural network, or SNN. To really get this, just think about your own brain. Your brain doesn't process information in this continuous smooth stream. It actually uses discrete synapses firing or spiking at specific moments in time. An SNN is a biologically inspired AI that mimics this exact temporal signaling. It processes information through time-dependent spikes. Now, what's really interesting here is this key concept. Information accumulates until it hits a threshold, and that triggers a firing event. Why is this absolutely perfect for rivers? Because water flow is totally event-driven. An SNN is perfectly built to capture sudden, abrupt changes, like, say, a flash flood right after a massive rainstorm, because its very architecture is designed around these sudden bursts of activity over time. Section 3. The SNN-ET Super Team, the ultimate tag team. Now, as brilliant as the SNN is at understanding time, it kind of needs a partner when data is incredibly scarce. It needs the extra trees, or ET, algorithm. The researchers behind this actually designed a complex, hybridized framework and broke it down into an easy 1-2-3 pipeline. First, they gather environmental data and filter out the noise. Second, the SNN makes a preliminary prediction of the river flow, and that data is clustered. Third, the extra trees algorithm takes those SNN predictions and creates the final, highly accurate imputation. Let's look a bit closer at how steps 1 and 2 actually play out. So, breaking down step 1, the AI obviously needs data to learn from. The researchers tested 2 different scenarios. Scenario 1 used only ground-based observations, just basic rainfall and river flow gauges. But scenario 2, that integrated ERA5-Land data. This is high-resolution global climate data that includes complex variables like soil moisture. And Scenario 2 proved far superior because it provided this much richer, holistic spatial map for the AI to learn from, which drastically improved the model's accuracy. Moving into step 2, we run into this piece of tech jargon, the Gaussian Mixture Model, or GMM. But really, just think of the GMM as a sort of sorting hat for river data. River behavior changes completely during a flood versus a dry spell, right? So the GMM basically sorts the SNN's preliminary predictions into normal flow and high flow buckets. By organizing the data this way, the extra trees algorithm in step 3 can train separately for extreme events, instead of letting rare floods get mathematically washed out by everyday normal flows. Section 4. The ultimate data stress test, breaking the model. The researchers obviously wanted to know exactly how much missing data this hybrid AI could actually handle before it just broke down. So they took perfect data sets and artificially deleted data in 3 realistic patterns. They tested random loss, which simulates unsystematic glitches. They tested sequential gaps, simulating a sensor being broken for weeks at a time. And they tested a combination of both. Now, that combination pattern is the absolute hardest stress test, and unfortunately, it's also the most common pattern hydrologists face out in the real world.
So, how did the coupled model perform? The results are honestly staggering. The SNN-ET model maintained highly reliable, stable performance even when 80% of the daily streamflow data was missing. I mean, let that sink in for a second. Even with 8 out of every 10 days completely blank in that combination pattern, this brain-inspired AI could accurately reconstruct the flow of the river. And this brilliantly illustrates exactly why teamwork matters in machine learning. If we look at the KGE score, where a 1.0 is considered absolutely perfect, the data is pretty undeniable. The standalone spiking neural network scored a 0.806. The standalone extra trees scored a 0.753. But when they coupled them together into the SNN-ET superteam, the score jumped to an excellent 0.823. The hybrid model clearly defeats the standalone versions. It proves that blending the temporal awareness of the SNN with the robust decision-making of extra trees is absolutely a winning formula.
Section 5. Future Global Water Management. The global takeaway.
So let's zoom out from all the math and algorithms for a second. What does this actually mean for humanity on a warming planet? While the real-world impact is huge, this isn't just about Thailand. This framework is highly scalable to data-scarce river basins all over the world. By enhancing the reliability of our hydrological data, developing nations can really advance sustainable water resource management. I mean, having an AI that can reconstruct 80% of missing data means we can better mitigate the impacts of climate extremes, safeguard our water supplies, and ultimately save lives when disaster strikes. I want to leave you with this final, kind of provocative thought. We just saw how an artificial intelligence designed to mimic the neural spiking of a biological brain can successfully reconstruct missing rivers of data. It forces us to ask the question, if a brain-inspired AI can do this, how else can we mimic nature to solve our most urgent environmental crises? The answers might just be waiting in the biology all around us. Thank you so much for joining me for this explainer. Keep learning, and I'll catch you next time.